So welcome back to Physics 112. How are you? So in this lecture, we will finish Kirchhoff's law. And we will talk about the last part of the circuit, which is RC circuit. If we have time, we may do RLC circuit, but typically we don't have time to do that. That's probably in 2 weeks or so after exam 2. And then we will talk about a new topic, magnetism. Okay. So first I put not Discord, I put iClicker question just to encourage you to come to the class on time. So I received an email from one of your friends. He asked me whether we have Discord channel, and honestly, I don't know the answer to this question. So apparently the answer is you don't know, which the same also my answer to her. So in the past we had Discord channel, but it was discouraged, or it wasn't encouraged by the department, because during COVID, all of the learning happens online, and some of your parents or many parents are not happy. So we try to push everything in person, but I see a lot of good things from having Discord. You don't have to join the Discord channel. So the reason of this question, other than to encourage you to come to the class on time, is also to avoid duplicates. So if you guys have Discord channel that I'm not aware of, then we should only have one. I will not be on the Discord channel. Okay. I think it's a good idea to have a space for you to criticize me together. The TA, if you want your TA to be part of the Discord channel, then you should ask your TA and your LA. But I will not be part of it. It's for you. So you can collectively give me feedback. Any other question? All right, so let's finish the circuit. I came to the class early and I drew the circuit already. On Wednesday, we calculated, this one was small r, and I think we calculated, I don't remember exactly, 5-fold, and maybe this 2 amps right there. This example is taken straight from Prusel. The next question is, what is the power of the configuration? Do you want to do iClicker, or do you want me to do it? Because we had a lot of iClicker last time. I don't want to exhaust you. So what is the definition of power? What is the unit of power? Watts. Good. And people use power in different contexts. For example, in electric generator, like there is one in Lake Havasu. I think that generates 200 megawatts per day, something like that. Or no, megawatts is per second, so there is no per day right there. Okay. So power on the 2 batteries. Okay. So first, this is like another case where the sign matters. So you should note that for the right battery, the current goes from negative electrode to positive electrodes. So the power here is positive. Here, P power is positive. So it does something. For the left battery, because of the magnitude of the batteries and resistors, the current goes from the positive electrode to negative electrodes. So the power here, so this battery actually consumes energy. So you may think that that's silly, why battery consume energy? We do that almost every night. You go home, you charge your devices, your cell phone, computer. So this one means it consumes energy. So power is energy per unit time, and the unit is watts. Okay. And then energy, so basically the change of energy per unit of time. So change on energy is QV divided by delta T. For a constant potential, like here, 12 volts, 5 volts, then it's delta Q divided by delta T times V. And this one is equal to electric current. So this is how we derive P is equal to VI. And you shouldn't, sorry. One of your friend had a accident. So if you're involved in an accident, let me know. You can join the class by Zoom, but without serious excuse, you cannot join the class by Zoom. It's just the policy of the department. Anyway, so P is equal to V times I, not to be confused by V is equal to IR. But you can use that, V equal to IR, then this one is also equal to I square times R. Right? Anyway, for this question, you will only need V times I. Okay. So let's call this right and left. So for PR, V times I is equal to 12 volts times 3 amps equal to 36 watts. You get that? And then for P left, and here, in science, you're allowed to guess the sign. Like one example that I told you, like if I tell you my height is 5'6", you know that it's plus 5'6". Here, because Kirchhoff's law. Sorry, I've been mispronouncing his name. Kirchhoff's law, which is the second one. Then VI is equal to minus. This one you have to insert the sign yourself, which is 5 volts times 1 amp. Okay. So that's the answer, which is given in your, you don't have this yet, but the notes that I will upload tonight, this afternoon, will have those answers. And this is taken straight from your textbook. So just a recap, Kirchhoff's law is based on the work by Gustav Kirchhoff. I think he's a German physicist. Basically, the first law relates to conservation of charge. The second one, in a given loop, if you walk along a loop, in this case, I'm talking to a charge, if a charge walks around a loop, the energy difference is 0. You don't lose energy. So in a circuit, whatever thing that generated should be emitted. So the delta energy should be 0. So the power that the battery put in the circuit is 31 watts. So 31 watts, 36 minus 5 watts, which is 31. And then we use Ohm's law to express VI in terms of I and R, which is equal to I square R. With that equation, we can calculate the energy loss due to resistors. Okay. So when you have resistors, you get heat. Those are the energy that the resistors emit. So let's call this, instead of left and right, 1, 2, 3. Okay. So P all resistors is equal to the sum of I square times R. And we start from left to right. You guys know what this means, right? It means the sum. So this one equal to, let me just be explicit. So I1 square is basically 2m square, which is 4, times R1, 3 ohms. This one is equal to 12 watts. And then the second term is 5, 1 amp square divided 5 volts, which is 5 watts. And then the last one, what is the last one? You guys are so shy. Ah, sorry. Good. Excellent. Thank you. 1 ohm. Thank you. So it's 1 watts. So sometimes you have to be a bit more less shy. So Ohm's law actually was derived by, the name is Wheatstone, Charles Wheatstone. The reason why we don't know him because he's very shy. He, one time he gave in England at the time, or even since up to these days, they have lectures every Friday night. And Wheatstone had to give lecture and he was so shy, he ran away at the last minute. And then Faraday, because Michael Faraday is an amazing and charismatic person, he just replaced his be the last minute substitute, and he made a hypothesis that light is an electromagnetic wave, which is in the end, it takes us many centuries to prove that he's right. Wait, not many centuries, many decades. So that's one. But people like Wheatstone. So what end up happen is that we keep that tradition. So in Royal Institution, that's the name of the institute, like 30 minutes before the lecture, they lock the speaker in a room. So sometimes if you don't see me for 30 minutes, it's because physics department locked me, because we love Charles Wheatstone. Okay. Next is the last term, which is this resistor here. I is 3 amp. So don't be too shy. Okay. 3 amps times 3 amp square times the resistor, which is 2 ohms. This one is equal to 9 times 2, which is 18 watts. The sum is 12 plus 1 plus 18. I always forget the units. 19, wait. 31, sorry. So it's correct. How did I? Okay, so 31 watts. So the energy that the battery puts is equal to the energy loss due to the 3 resistors. So everything is consistent, yeah. Yeah, this one typically we don't put. For power, don't worry about the sign. But you should, in your when you understand the material, you shouldn't think that you generate 31 watts by running your cell phone, for example. This one doesn't generate energy. It consumes energy and it emits light and heat and sound, right? You can put sign if you want. Yeah, are you happy? Okay. Any other question? Excellent question. Yeah. Yeah. So first you need to know the magnitude. You cannot just guess. After we do all this exercise, we know that one of them, the current goes into, like it hits the positive electrode first. Basically, you run it in reverse. It's like charging your cell phone using wires. The other one, it hits the negative electrode first. So the current flows through the proper way. So this one is plus, this one is negative. Okay. Any other question? Yeah. They will, the sum has to be the same value because the power in is equal to power out. This is like if you go to a river, I know we are in Arizona, in the middle of a river is like a wire or a circuit. In the middle of a river, water cannot just disappear. Or you cannot just get a lot of water when you like walk across the river. Yeah, P out. Well, this one, basically, if you sum all of this, so P of the battery, the energy sources are two batteries, and you lost heat due to resistors. So P out due to the batteries is equal to P due to the resistors. Good. All right. Somehow I lost. Okay, so this is what I'm testing your memory here. So what is the? Let's just spend like 20 seconds. What is the fluid mechanics analog of a capacitor? Right. Okay. So let's not take too much time. So please enter your answer. So the hint is in the right whiteboard. Okay. So let's stop. So what is the analog of a capacitor? Water tower. So a circuit is like a river, basically. That's a good analogy. So a circuit comprises or contains resistors, capacitors, and we will talk about inductors and batteries. For capacitors, the analog is water tower because capacitors store energy. Okay, so what we will talk about in the next few minutes, get the time, is the energy loss or the movement of charges in charge capacitor. Right? So I find this analogy helpful. I'm not sure about you, but if you have a water tower, basically you store energy. In capacitors, what they store is charges. depending on the size of water tower, the rate of flow of water or the time requires to empty water tower depends on the size of the water tower. You get it? I'm talking in circle. I get it. And also the size of this hole here. So this one, you can view this tubing or this opening as the resistance. Okay. So this one is the capacitor. So the larger the water tower, it will take longer to empty the charges, to empty the water. And the larger the resistance, which means the smaller the hole, the smaller the opening, it takes longer to empty capacitors. Yeah. Dinush. Huh? Yeah, you can use different analogies. Thank you. Good. Okay. Water tower. Any other things that can store energy? Okay. All right. So basically, if we have a capacitor, then you can store charges. You can put it Q or Qi, and then if you start with a closed circuit meaning you break the circuit. Sorry, an open circuit means that there is a charges cannot flow, and typically we have resistor here. So at this point, these charges, they would like this one, the positive charges would like to, they get attracted by Q, but because there is a vacuum in between or an insulator in between, these charges cannot be closer to Q. So they are dying to see Q. Today is Valentine, right? Maybe my wife will come. I don't think it's gonna happen. We have 2 kids, so we're done with those things. But who knows? She may surprise me. Okay, so this guy is dying to see minus Q. So this boyfriend is dying to meet his girlfriend. So this could work when we close the circuit and it will discharge the capacitor. Okay. In your textbook, Q is fixed, but small letter I or Q means the charge as a function of time. So we don't, in this class, we don't write T because Q is a constant. And this is a non-calculus based class, so I'm not gonna derive the equation. But discharge, so initially the charge is Q. This is when the circuit is open. And then as soon as you close, the charge will decay exponentially. And you've seen this exponential equation in many places in science, like radioactive decays. When I boil water and I let it cool down, it follows this equation. So Q is equal to initial Q. Oh. This is this is where we are. Sorry, what did I do last night? Okay, so instead of talking about Q, let's talk in the context of I. So similarly for I, initially at t equal to 0, I is a constant, but the current as a function of time, you know that I is equal to delta. Apologize for the confusion. So this one, the current as a function of time decays exponentially decay, so minus t divided by a time constant, which is r times c. Okay. You know what this number is? This E Euler number. Do you know this? Okay. And you know what is E or any number to the 0? 1. Okay. So I is equal to, basically time dependent currents as a function of at t equal to 0 is equal to I, or your textbook add I naught. No, your textbook doesn't add I naught, or your textbook add the subscript. Okay. How about e to the minus infinity? It's 0. Okay. So this is math that you should know. So basically, if you wait long enough, I'm just going to use this, but it's basically approaches infinity. So what is this? E small, the time dependent current, or small I, is equal to I naught times E to the minus infinity divided by RC. So currents at infinity, if you wait long enough, is equal to 0. Okay. So it takes infinite amount of time to empty a capacitor. So, and then typically what people, so we need to come up with a criteria, meaning like what is the, when you talk to like between scientists or engineers, you need to come up with criteria so you can communicate. So in the end, what we decide as a time constant is when I, so it started at I naught and then ends at 0, when I is equal to, when I say I is time dependent current, is equal to I naught divided by E. Then we call this time as tau, or time constant, which is RC. Okay. So in order for I, so time dependent current, you can put as a function of t is equal to I naught divided by E. Then this formula here is equal to I naught divided by E. In order this equation to be correct, then T has to be RC. So if you put, let me just write it. Right? Then you get I naught E to the minus 1 is equal to I naught divided by E. Okay. So in the exam, we will ask you about this time constant, RC. So basically, coming back to this analogy, the larger the water tower, the larger C, it takes longer to empty this water tower. So let's write the same. So the time constant, which is equal to RC. So the larger the water tower, the larger tau. And then in the exam, I may ask you which one that has the faster rate. Then you need to find conditions such that tau is smaller. Okay. Faster means higher or lower tau. So faster dynamics will look like this, right? That means this tau here is smaller than this one. And then slower means RC has to be bigger. So don't just fixate it to whether the number is bigger or lower, but try to understand what this time constant means. And this, for example, this resistor here is the opposite of the size of the opening. The smaller the opening, the more resistance that the water experiences. Any questions? And then the rest are basically similar. If you charge an RC circuit, the plot, instead of when you charge something, and when you charge, let's say when you fill water to the water tower, you start with empty water tower or empty charge, and then it will approach to maximum capacity. This one is QC times V, or Q final, which is C times V. And then the equation, instead of using Q final, we use small q as a function of T, which is equal to Q final times 1 minus E times divided by the same time constant. So let's use this mathematical rule that we just review. Q at T is equal to 0 is equal to Q final times, in a bracket, 1 minus E to the 0, so it's equal to 0. And Q, if you wait over a long time, is equal to Q final times 1 minus E to the minus infinity. Let me just write it down. Minus infinity divided by RC. And this one is equal to E to the minus infinity is equal to okay. Good. So 1 minus 0 is 1, and then this one is equal to Q final. Okay. Easy? It's the easiest A on campus. Okay. You just put T is equal to infinity, T is equal to 0. All right. So I think the rest you can. So in the lecture notes that I will upload this afternoon, I will put more neuroscience. Those things will not be on the exam. They are for you, all those calculations. But basically, we use the concept of capacitors for, let's say, neuroscience. More than half of my lab, we study membrane biophysics. So we use this concept all the time. It's also the core, like the foundational science of my startup. You want to do iClicker? All right, so we have the first one. All right, what is the correct charge versus time for a charging RC? Okay. So there is charging, there is also discharging. All right, so basically almost all of you answer the question. What is the answer? The answer is, what is the answer? B. So when you charge, you start with 0, and then you end up with a full water tank, a full capacitor. When I say full, it's actually close enough to full. Because if the capacitor So see, if you put more and more charges to capacitor, every time you add more charges, there is repulsion due to these charges. So it will be more and more difficult. Okay. There is less space, more electrostatic repulsion. So it takes longer and longer. Okay. Next is this concept. This question combines RC circuit. So the formula is the time constant is equal to RC and capacitors. Okay. The equivalent capacitors for series is and for parallel C equivalent is equal to C1 plus C2. Okay. So this question is asks, so there are two circuits, one of them is series, the top one is series, the bottom one is parallel. The question is, in which of the two circuits shown above will the capacitor store more charges? So that's first, which is, you just need this equation. Sorry, I haven't clicked. Okay, so basically 10 more seconds. 5, 3, 2, 1. So what is the answer? B. So basically you want to find the arrangement with larger C equivalent. Okay. It's B, really nice. Next question is relates to the time constant tau. So you need to pay attention here. In which of the two, so the circuits are the same. In which of the two circuits shown above will the capacitor charge more rapidly? Charge more rapidly. More rapidly, that means larger constant or smaller constant? When somebody says, let's use this one. Which one is more rapid? The one on the right or the one on the left? Left, right? And this one, which one is bigger? Tau prime or tau double prime? This one is faster. So what you want is you want to find a circuit with smaller time constant. Basically, almost all of you answer. 5 more seconds. 3, 2, 1. Okay, so the answer is, so smaller tau, if you keep the resistance the same, that means you need arrangement, you need to find arrangement with smaller C equivalent. And then you reduce the capacitance by arranging two identical capacitors in series. Okay, so basically, almost all of you got it right. Really easy. So how easy is this class? I'm still puzzled by your exam because your iClicker scores are really good. So let me tell you one thing that I haven't done this year. Some students didn't like it, perhaps because of my broken English. Tell stories. So maybe, and then if you want to leave, you can leave because of my broken English. The doors are right there and right there. So to prepare this lecture, I typically asked my wife, like the night before, I asked her, like, what are the jokes that I should say to begin my class? And then she said, like, whatever. Uh, whatever your joke is, make sure you don't make fun of pre-meds. And then in my head, I just say, aha, time for trouble. Uh, so so last night I start pitching, like come up with many jokes, and this is like typical me. None of them she found funny, so I'm gonna tell you one of them. That's all I have. But if you don't find it funny, you're correct probably. And that's, but this is the best one that I had, which leads to something really maybe profound. So just, but if you don't like it, the door is right there. So I asked her, like, oh, so we will talk about magnetism right now. It's a new topic. It's a fun topic. It's the physics behind why we have life on Earth. The answer, one of the answers is water. The other one is because the Earth has magnetic field, and that thing relates to aurora, which is one of the most beautiful things, phenomena on the Earth. So anyway, before we talk about magnetism, so I asked her, who you think first discovered magnets? And then she was like, I don't care, I have one notes. Same answer. And then I told, and then my answer was, it's world's first shopkeeper store guy. He discovered it when he tried to put decoration on people's fridges. And she was like, yeah, it's not funny. Ask your son, he will say that it's not funny. But that thing is actually led me to ask Google, that I didn't know the answer to that question. Who gets credit for finding or discovering magnetism? Anyone knows? Like a good guess would be Aristotle, Galileo, or Plato, or those people in Greece. And I'm sure people in Greece have found magnetism. But the person that get the most credit is actually a physician. See? It relates to half of the class, which are pre-meds. Turns out that a physician, many physicians, or perhaps half of them, find physics is easy, and they even change physics for good. So in physics, every time we think that we are done with physics, somebody come up with an experiment that proves that our theory is not enough. So we need to modify it. And that's the reason why we're studying magnetism, because many things that I'm gonna tell you in the next few minutes cannot be described by Coulomb's law. So who is this physician? Anyone knows? Anyone knows? His name is William Gilbert. He's not from Arizona. He's not from Gilbert. He's actually from. I assume he's from well, he did his medical degree in University of Cambridge. So he was a physicist. When if you Google his name, you will. Wikipedia says that he's a physicist, but he's actually a really accomplished physician. So he was that famous. Queen Elizabeth I asked him to be his doctor. Apparently, he's not that good, because Queen Elizabeth passed away 3 years after he became her personal physician. But he was retained by the successor. I don't remember, like Prince something. Okay. So in his time, so he wrote a book. I think the book was published before 1600. I don't remember exactly the year. And there are 60 copies of that book, 60 or 90, I don't remember exactly. So Amazon didn't exist, so it was considered as a bestseller at the time. But and then I read more. It turns out that there was one person that William Gilbert often cited in his book. His name is Pierre de la Cour. So he was an army. Uh, he was an army. He was a soldier and also a theologian. And his letter, he made 30 copies of the letter, which in 1200 year of 1200-ish, it was again another smashing success. And then the thing that happened is that turns out that William Gilbert owned one of the copies, and that's the reason why it triggered him to learn more about magnetism. Another interesting thing that I learned last night is that the only bequest of Queen Elizabeth I, before she passed away, is to give funding for William Gilbert to study magnetism. So that's how exciting magnetism at that time. Okay, now everything is magnet. I'm like this thing. Magnets. All right. So what did he do? So he showed that magnets can lift magnetic materials. So that's one thing. He also, William Gilbert also showed that Earth is actually a giant magnet. So we know that. And this thing is actually important. The reason why there is life on the Earth is because this magnet turns out trap many charges from the sun. So a long time ago, there was fascination with Venus because Venus has similar size, similar enough in astronomical sense temperature as the Earth, but because Venus lack magnetic field, it's actually miserable. I mean, if you want to live in Venus, then good luck. There are a lot of charges that will hit you every day. There are other things that we will do demo. So I want to incorporate more demos because it's more fun with magnets. One is the first demo is probably by Orsted, that he put compass. So compass, we know that compass is basically a magnet. It has north and south poles. And then he put cable on top of compass, and then nothing happened. Right now, nothing is surprising. You can explain it with probably Newton's second law. There is no forces, then there is no movement. But one thing that Orsted did, he flow charges, he flow currents. And then what happened is this magnet becomes like this, switch to this, so it rotates to the left. Okay. So this was surprising. So in physics, if you do something and then people cannot explain with our current understanding, people get very excited. So what is the difference between with and without current in the system? Because without current, when I say with current, is this guy connect the circuit with a battery. In terms of charges, what is the difference between before or after you connect the circuit with a battery? I'm not going to finish the class until you answer. I already called AS to security. They locked the door. Okay, some of you must. Okay, yeah. So it turns out that what you will learn on Friday and in the next few weeks is that in order to experience charge magnetism, you have to move. The charges have to move. I think that's all I have. Any questions? All right, I'll see you on Friday. Yeah. Go ahead, sorry. I need to take care of this. You want to wait in that room? 186. PSF 1. Yeah. Yeah, you can wait. You can wait there.